So today, our second problem will be also on truss problems. Here we have truss, as you can see, consisted of 5 members, and the requirement of this truss is to find the stiffness matrix K for the whole truss, assuming that the area of each member is 0.0015 meter square and the elastic modulus E is 200 gigapascal. The second requirement is to determine only the vertical displacement at node 4, which is the bottom node in the middle, and the force in member 4, where A similar to the previous part. Okay, so here we need to do same things as we did in the last problem, and I will share my whiteboard screen now. So we have question number 2. So in this question we have plus we have 5 members of this truss and 4 nodes. This support is hinge, this support is a roller support. So the numbering is, we have this is node 1, this is node 4, this is node 2, this is node 3, this is member 1, this is member 2, this is member 3, this is member 4, this is member 5. Okay. This is the degrees of freedom we have. How many degrees of freedom? We have 5 nodes or 4 nodes. 4 nodes, so we have 8 degrees of freedom. This 1, 2, 3, 4, 5, 6, 7, 8. The dimension we have here are 4 meter, 4 meter, and 3 meter. We have only one force here at node 4, which is 10 kilonewton. If you look at the problem, we have this is the direction of the members. This is member 1, this is member 5, this is member 2, this is member 4, this is member 3. You don't have to be similar to this, but if we can follow this example. Okay, so it is given to us that the area of these members are 0.0015 meter square. The elastic modulus is 200 gigapascal. To make it easier for us, I will convert this to millimeters. So A will be 0.015 meter square. To convert to millimeter, I will multiply by 1000 square. So this will be 1500 millimeter square. E is 200 times 10 to the power 3 Newton per millimeter square or megapascal. The dimension will be 4,000 millimeter, 4,000 millimeter, 3,000 millimeter. So all our dimension in this problem are in Newton and millimeter, just to make it easier and to follow the previous example. As you know, this is our y-axis and this is our x-axis. So if we consider this node is our origin, so node 2 is 4 and 3 meters. This node is 4 and 0. This node is 8 and 0. So this is our coordinates as well to help us in calculating the cosine theta x and cosine theta y. Now, the requirement is to determine the global stiffness matrix of the truss K cut. The second requirement is to only determine not all the unknown, determine the vertical displacement at node 4 or at joint 4 and member force in member 4 as well. So this is our requirement. Before I start, just I will do it in the beginning. How many members we have? We have 5 members. How many joints or nodes? We have 4 nodes. How many degrees of freedom? We have 4 nodes times 2, so it will be 8 degrees of freedom from D1, D2, D3, D4, D5, D6, D7, D8. So 8 degrees of freedom. What we know from our supports? From our supports, we have 2 supports here and here, right? So we have here this 1, 2, 3, 4. If you notice the numbering start with the unknown degrees of freedom. So we have from the support or from the boundary condition, these two are 0 because it is hinge prevent the vertical and horizontal displacement. Here, this only 0 because this is a ruler, so the movement 5 is allowed. So how many unknowns we have here? 5. So from boundary condition, we have D6 equal to D7 equal to D8 only equal to 0. But from D1, D2, D3, D4, and D5, all of them are unknowns to us. Okay? So this is just a quick notes before we start our solution. Okay? Now, just a reminder that this is a truss element, so K truss, because this is what we are dealing with again, EA over L, this is the stiffness matrix of a truss, times lambda x squared, lambda y squared, lambda x squared, lambda y squared, lambda x, lambda y, negative lambda x squared, negative lambda x, lambda y, negative lambda x, lambda y, negative lambda y squared, lambda x, lambda y, and it is symmetric here. So this part is here. So this is our truss stiffness matrix. And we need to construct the stiffness matrix for the 5 members we have from member 1 to member 5. So now I'll save this one. So now for member 1. For member 1 is this member. Start with node 1, end at node 2. The displacement we have 1, 2, 7, 8. Okay. This is the direction of the member. As you know, the dimension given to us, this is 4,000. This is 3,000 millimeter. Given to us, A equal to 1,500 millimeter square. E is 200 gigapascal, so 200 times 10 to the power 3 megapascal. L will be root 4,000 square plus 3,000 square, so it will be 5,000 millimeter. So this is all the data we need. Now we need to find lambda x and lambda y. If you remember from previous step, this was our origin, 0 and 0. This was 4 and 3. Okay. So lambda x will be x2 minus x1 divided by L. Y2 minus y1 divided by L. So it will be 4 minus 0 over 5 will be 0.8. This will be 3 minus 0 over 5 will be 0.6. So now we have all the data needed for K truss. Sorry, K for member 1. So K for member 1 will be A times E over L. I will leave A times E as constant without substituting in it because it is all similar. So we'll try to do it like this over 5,000, which is the length. This will be times 0.8 square, 0.6 square, 0.8 square, 0.6 square, 0.8 times 0.6, negative 0.8 square, negative 0.8 times 0.6, and so on. I've done this before. This one is negative 0.8 times 0.6, negative 0.6 square, 0.8 times 0.6. This one is 0.6 square. This will give us A E over 5,000 times 0.64, 0.36, 0.64, 0.36. The important thing is this is movement 7, movement 8, movement 1, movement 2, movement 7, movement 8, movement 1, move 2. So this is our important part. This is our important part in the stiffness matrix. 8, 7, 7, 8, 1, 2. If we complete this part, so it will be 0.48, negative 0.64, negative 0.48, negative 0.48, negative 0.36, 0.48, 0.48. So this is the stiffness matrix for member 1. For member 2, how is member 2? Member 2 is similar to member 1, but in the with a different reversed slope. So this is member 2. What we have in member 2, we have here movement 1, movement 2, movement 5, movement 6. This is node 3, this is node 2. This is the direction of node of member 2. Here is our dimension, 4,000, 3,000 millimeter. The coordinates of this node is 8 and 0. Here is 3 and 4. Okay, so what we have here, if we write down our dimension, A, E, the length will be again the root of this 2. So it will give us 5,000 millimeters, which is 5 meters. What is next? Lambda x and lambda y. Lambda x will be, the start is 3, so 8 minus, sorry, this is 4 and 3, not 3 and 4. Okay, because this is x, we start with x, and second is y. So this x and this y. So now we have 8 minus 4 over 5, which is 0.8. Here will be 0 minus 3 over 5, which is negative 0.6. If you, because all of this, because in this problem, the direction was assumed to be from 0.3 to 0.2. If you start with 0.2, it will be reversed, but just to follow this example, so this is our the value of our lambda x and lambda y. Now, this is K2. So we have EA over L. L is also 5,000 times. What is the movement we have here? 5, 6, 1, 2. So 5, 6, 1, 2. Again, this is because we start with node 3 and end at node 2. So that's why 5, 6, 1, 2. So what we have here, this will be 0.64, 0.36, 0.64, 0.36. Here we have negative 0.48, negative 0.64, 0.48, 0.48, negative 0.36. Here is negative 0.48. Here is negative 0.48. The main part for us in this is 1, 2, 1, 2. So it will be this quarter, because this is the related part to the unknowns. So similar things we will do in case 3 or member 3. Member 3 is a horizontal member, the one to the right side. Start with node 4, end at node 3. This is the direction of the member. This is the displacement at node 4, 3 and 4. This is the displacement at node 3, which is 5 and 6. The length of this member is 4,000 millimeter. So A is 1500 again. E is 200 times 10 to the power 3 megapascal, and lambda x, lambda y. Lambda x will be, this node is 8 and 0. This node is 4 and 0. So it will be 8 minus 4 over 4 will be 1. Will be this one, 0 minus 0 over 4 will be 0. So this is our lambda x, lambda y. So now k of member 3 will be EA over 4,000, which is the length, times, what are the movement we have here? We have 3, 4, 5, 6, 3, 4, 5, 6. So we have here lambda x squared, which is 1, 0, negative 1, 0. This is all zeros. This is negative 1, 0, 1, 0, 0, 0, 0, 0. The part we need here is, because 3 and 4 also unknown, so the main part here is this part, 3, 4, 3, 4, and also 5 is unknown, so 5. So here as well, we will need 5, because 5 also unknown, so we need this part. So because 5 is unknown, sorry, I forget that 5 is unknown, so we have any parameter related to 5 will be with us. So this one is negative 0.64, negative 0.48. Okay, here we need also anything related to 1, 3, 4, and 5. So we have this part. Okay, so now we have K3 also ready. We still have member 4 and member 5. As you can notice, member 4 is quite similar to member 3. So member 4 we have, which is also a horizontal member. This is member 4, but the direction was assumed to be the reverse of member 3. This member start with node 4, end at node 1. The movement we have is movement 7, movement 8, movement 3, movement 4. These two are unknowns. The length of this member is 4,000 millimeter. The coordinates is 4 and 0 and 0. So A will be 1500 millimeter square. E is 200 times 10 to the power 3 megapascal. Lambda x and lambda y. Lambda x will be 4 minus 0 over 4 would be 1. Lambda y will be 0 minus 0 over 4 will be 0. So lambda x is 1, lambda y is 0. Okay, now we can construct the stiffness matrix for member 4, which is K4 equal to EA over L. So it will be EA over 4,000 times, what is the movement we have here? We have 3, 4, 7, 8. 3, 4, 7, 8. So we have this is our members. Here we have lambda x is 1, lambda y 0, lambda x 1, lambda y 0. So this will be anything related to lambda y will be 0, -1, 0, all of this 0, all of this 0, -1, 0, 0. Okay, we have again these two are our unknowns, so we are focusing on this part 3 and 4. If we just need to get the unknowns. Now the last member is member 5. Okay, now for member 5. Member 5 is a vertical member. If you have a look on member 5, this is our member number 5. This is the direction of member 5. Member 5 start with node 4 and end at node 2. Member 5 has 4 degrees of freedom, 3 and 4 at the bottom, and 1 and 2 at the top. The length of member 5 is 3,000 millimeter. The nodes are 4 and 0 and 4 and 3. Okay, so now A equal to 1500 millimeter square, E equal to 200 times 10 to the power 3 megapascal. And we have lambda x and lambda y. Lambda x will be 4 minus 4 over 3, which is 0. 0 minus 3, sorry, 3 minus, we start with the end. So 3 minus 0 over 3, which is 1. So this member, lambda x is 0, lambda y is 1. So if we substitute to get K1, K5, so K5 will be EA over 3,000 times, what is the movement we have? We have the start is 3 and 4, and end is 1 and 2. So 3, 4, 1, 2, 3, 4, 1, 2. This is our displacement, displacement, and this is our stiffness matrix we need to get. So we have here anything related to lambda x will be 0. So this will be 0, this will be 0, this will be 0, this will be 0. All this has lambda x. Lambda x also 0 here, so this will be lambda y square, lambda y square. This lambda x negative lambda y square, lambda x negative lambda y square. So this is our stiffness matrix for member 5. Because we have all of them, 1, 2, 3, 4 are unknowns, so we need to, all this stiffness matrix are needed to calculate our unknowns, because this member contains the 4 unknown degrees of freedom, 1, 2, 3, and 4. Okay, so now we have constructed the stiffness matrix for the 5 elements, the 5 members. Okay. Now I will stop sharing and stop the